Let's take a look at a more complicated scenario where we may not know the resistance of some object, but we know the voltage and current that is passing through it. And so, as before, we're going to look at our voltages and currents as time-based functions. And so we might have some sort of voltage that is passing through here, and our voltage is going to have some sort of magnitude. So that is our Vm component. It is going to have some sort of frequency, and then it is going to have some sort of phase. And so what the phase is going to indicate is the amount of time sort of between time zero and the peak of that wave. And in the same way, we can have a current function as well. And so just like with our current, it would be something over time. And that, let's maybe make it come in at a little different time here. This would be our current function. And our current would have a magnitude as well. So it would again have its own magnitude. It would have its frequency, and it would have again its own phase. And that would be the amount of time from zero to a peak of the current function. And remember, when the voltage and the current are out of phase, that is due to our large inductive and reactive elements in the circuit that bring those two waves out of time. And so now we can go back to sort of our traditional definition of what power is and say that, well, power over time is always voltage over time times current over time. And now we have sort of our more complex descriptions of what these two are. So our voltage over time is Vm cosine Wt plus the voltage phase times the current and its own frequency plus its own current phase. So this is going to be phi I, and the other one is going to be phi V. And when we multiply these two together, again, we're going to have the same problem as before when we have two sort of cosine functions multiplied. But we have another trig identity that we can use that says if you have the cosine of some object times the cosine of another object, then the result of those two is 1/2 cosine of x minus y plus 1/2 of cosine of x plus y. And so applying that relationship to this power, this function here, we end up with Vm Im over 2, because that's the 1/2 piece. And then this would be cosine of the voltage phase minus the current phase plus, and then we'll just get this relationship out of the way, plus Vm Im over 2 cosine of 2Wt plus phi V phi I. And so, not that we'll ever demand you do this math on a test, but one thing to see is that this function right here varies in time. So this is a sinusoidal function. So if we go back and we say, well, what is the average power of this P of t function here that we've come up with? This average on this will eventually be 0. Whereas with this object here, this is actually sort of constant in time, and so this will be our constant value for average power. So another way to look at average power is that to say average power is Vm Im over 2 cosine of the voltage phase minus the current phase. And so we had our previous expression that was 1/2 I squared R. That is also correct, but this is another way to look at it when I don't maybe know the resistance of an object, but what I do know is more important. I know what is the phase of my two waves, and then I end up knowing the magnitude, the voltage magnitude passing through it, and the current magnitude passing through it. This will also give us a measure of average power, and this average power is, like all other real powers, going to be measured in terms of watts. So we'll see in a bit with reactive power that we have to come up with new units, but for real power, our units are still in the conventional watts.